My name is Dr. Bahram Farahmand. I am a lecturer at the University of California in Irvine and also former Boeing Technical Fellow. I will give a series of lectures in the different areas. Let me just briefly tell you about my areas of expertise or experience that I got through industry, mainly from Boeing Aerospace and also academically. High cycle and low cycle fatigue, and elastoplastic fracture mechanics. I'm going to read it from here now. Elastoplastic fracture mechanics, physical and virtual testing for material characterization of metallic and composite material. Metallics are isotropic and homogeneous mainly, and composites are not homogeneous and anisotropic. NDI inspections, different types of NDI inspections, fracture stir welding as well as fusion welding, repair of both metallic and composite materials. We will talk about how to do the repair through fracture stir welding. And separately, also, we'll talk about the repair of composite that went through some kind of damage. Additive manufacturing, we'll talk about additive manufacturing, which I taught a graduate course on that, and many others. I prefer to go through short lectures, like probably 10 minutes. And it is much better to do it that way, because to go through 1 hour of lecture, audience may not going to enjoy it. They may get tired, bored. So it's much better to go through the way I just described, short videos for areas that I just mentioned. So having said that, I'm going to go first through the linear elastic fracture mechanics. And so I'm going to start by doing that right now. The discussion would be on linear elastic fracture mechanics. This is a strong tool that can be used to assess the behavior of defects in the structural part. So when the structural part is subjected to a load-varying environment, that means an environment that is cyclic in nature or fluctuating load, that's another term to use, then it would take some number of cycles for crack to initiate from the damage, grow in a stable manner until it reaches a critical value. We don't want to get to that point. So therefore, we are going to use linear elastic fracture mechanics analysis to find out how many load cycles does it get in order to get to that final point or critical point or failure point. That is important because when it reaches that point, that structure or structural part, structural components, it's going to fail. It's going to go through damage. It's going to be useless. And God forbid, it may cause loss of life. And we don't want that to happen. So we are going to use linear elastic fracture mechanics to assess the behavior of defects in the material. Having in mind that all materials have defects, macroscopic in nature. They go through inspection, comprehensive inspection. But yet there are defects in the structure that when the structure is exposed to the, as I said, the load environment, the crack is going to initiate in a stable manner and propagate. When I say a stable manner, not all materials, they go through that stable crack propagation. It depends on the nature of the material. Material could be brittle, could be semi-ductile, could be ductile. If they are brittle, then as soon as the crack opens, it's going to go catastrophic. It's going to go fast and cause failure. As a matter of fact, the linear elastic fracture mechanics was established for brittle material, but then later it was modified for material that shows some amount of ductility. And I'm going to add that in aerospace or aircraft, they never use materials that are brittle. For example, aluminum is not brittle. Steel is not brittle. Titanium is not brittle. They have some ductility, and they have to have some ductility. And so for that reason, linear elastic fraction is going to be helpful. It's going to be modified to some extent. And next time I'm going to talk about this topic, interesting topic, in more detail.